Welcome back. We will now discuss another symbol, another tensor notation or symbol. We call this the conical delta. Conical delta notation. And it is written as the name implies as delta. Okay. So we will make use of this in also presenting some definitions and doing some analysis as we proceed. It just makes our work easier. Use of these symbols make our work easier. We can do almost all of the things we have to do without them. Okay, but knowing these symbols and the meaning and how to play around with them actually makes the work easy, especially when we want to prove relations, vector relations, as we will do in this course. So, say that if you have the conical delta, it usually comes with two subscripts. So, let's say it comes with subscripts I and j. What is the meaning of this delta notation here? This is going to be 1, so I'm just going to write this out so you can see it as some piecewise defined function. It's going to be 1 when I equals j and 0 otherwise. If I is not equal to j, then it is 0. So you might be wondering, what is the meaning of this? How did we come about this? It is a notation. Now the idea is that all of these things or this particular one comes from observation. That is, we observe a pattern in some relation and we say, okay, we can better model this pattern by using this symbol instead, so that whenever we come across this symbol, we're able to interpret it correctly. That this is the implication of this symbol, and so this is what this result will give us, and you will see all of these things in action as we proceed. Okay, so for now, you may see this if you really want to better relate with this. You may see this as an expression that tells us the term or some term or any term of an identity matrix. If you know what an identity matrix is, fine. If you don't, you should. That's also fine. For instance, we have a 2 by 2 identity matrix. We say that that is going to be the matrix 1, 0, 0, 1. So if I and j represent the position of a certain element here, we know that if we have this expression here, this is on the first row, okay, and the first column. So this is A11. So because the subscripts are the same, that means in this case the subscripts I and j are the same. I is equal to j, and because of that, the element is 1. So that's what we mean by that, that you can see this as representing an arbitrary element of an identity matrix. So if I and j are not equal, for instance, in this case, this is going to be row 1 and column 2. So this is A12. A12 obviously is 0 because 1 and 2 are not equal. If you come here, this will be the elements in row 2 and column 1. So 8 to 1, they are not equal. 2 and 1 are not equal. So that element will be 0. And if you come here, this is the element in the second row and second column. Because 2 and 2 are equal, then this will be equal to 1. So we say that this delta ij is that expression that implies that we have a number that will be equal to 1 if the subscripts are the same, and it will be equal to 0 otherwise. Okay, so now I need you to pay attention here. If we have, let's say, delta 1 2, what do you think this will imply then? If this is the conical delta, we have delta 1, 2. That means this is going to be equal to 0. Why? Because 1 and 2 are not the same. If we have delta 2, 2, okay, that will be equal to 1 because 2 and 2 are the same. You know, of course, we're still dealing with the subscript here will still be for our vector discussion, it will still be from 1 to 3. Okay, so if we have delta say 2 3, that will be 0 obviously. If we have delta 1 3, it will be 0 as well. If we have delta 3 3, we know that will be 1 because in this case the subscripts I and j are equal. Okay, so that is the definition of the conical delta. It is equivalent to 1 when the two subscripts are the same, and it is equivalent to 0 otherwise. Okay, So what if I have something like this now? If I say that a certain expression is equal to, say, delta I, what do you think this is equal to? Think about that for a moment. If I write delta I, you might be tempted to think that this should be equal to 1. Now, if you say this is equal to 1, you are wrong actually, but your wrongness, so to speak, or the error, so to speak, will be excusable or understandable. Okay. The reason for that is that you might look at the definition and say, okay, when I and J, when the two subscripts are the same, this should give us 1. Okay. So in this case, you have the two subscripts to be the same in quotes now. They are I. So you might think this is 1. But that is not correct. That is not an appropriate thing to do. You only do that when you have actual numbers here. Okay, like we just did now. If you have actual numbers there, yes, that is 1. But if you have just some arbitrary subscripts like we have here, let's say it's data JJ, data II, data KK, then it is not 1. And the reason for that is because having double subscripts, this is like a repeated subscript. So you have I subscript I subscript I. This is repeated subscript. So because of that, this by our Einstein summation convention that we've discussed already, that's why we discussed that first. We know it means a summation, so it has to be summed over because this is a repeated subscript or a subscript that appears twice in the same term. So this is essentially implying delta 1 1 plus delta 2 2 plus delta 3 3. So this will then be equal to delta 1 1, which is 1, plus 1 because the two are the same, okay, plus delta 2 2, which is 1, plus delta 3 3, which is 1. So this is basically equal to 3. So surprised, but don't be surprised. That's exactly what it is. It is going to imply 3 when you come across it, okay? So that's very, very important, please. It is when you have actual number that you make this interpretation as it is here. Just move ahead. But if you have this thing like this alone, written alone like this, and you have this subscript to be repeated, please and please, this is going to be the implication of it. It has to be expanded out this way. Okay. Now, what if you have, let's say you have some other expression written with this Kronecker delta symbol. So for instance, you can have, let's say, some other expression. Let's say you have AI delta IJ. What is the implication here? If you have AI delta IJ, now pay attention. By the Einstein summation notation, we can see that I appears, okay, twice. So I is definitely a dummy subscript here. So because it is a dummy subscript, it has to be summed over from 1 to 3. So that means this is going to be A1 delta 1 J. J is free because it appears only once, okay? Plus A2 delta A2 please, A2 delta 2, okay, J plus A3 delta 3J. So what can we say about this? What implication does this have on the entire combination? So looking at this now, we see that this here this expression right here is going to give us, if j is equal to 1, this expression here will become 1. I mean, if j is equal to 1, this will be delta 1 1, okay, and that will give us 1. If j is equal to 2, now pay attention, let's take that one after the other. Okay, let's consider the cases one after the other. If j is equal to 1. We know that this is a free subscript. It means it can take on one value at a time, one value from 1 to 3 at a time. We discussed that already. So if j is equal to 1, then this expression will be, we're going to have for this expression a1 delta 1 1 plus a2 delta 2 2, sorry. J is equal to 1. So that will be delta 2 1 plus A3 delta 3 1. So by our definition of the delta, okay, the Kronecker delta, we know that because 2 and 1 are not equal, this is 0. Because 3 and 1 are not equal, this is 0. So at the end of the day, this will just be A1 delta 1 1. Delta 1 1 is 1. So this is just going to be equal to A1. And similarly, if j is equal to 2, what are we going to get from this result? That means that will be A1 delta 1 2, okay, plus A2 delta 2 2 plus A3 delta 3 2. And what will this give us now? Delta 1 2 will be 0 because 1 and 2 are not the same. Delta 3 2 will also be 0 because 3 and 2 are not the same. So at the end of the day, we have A2 delta 2 2 left. And of course, delta 2 2, because 2 and 2 are the same, is 1. So at the end of the day, this gives us just A2. And similarly, as you might guess already, for the same reason, and indeed you can convince yourself that this is going to give us A3 when j equal to 3 for the same reason, because this will be delta 1 3, delta 1 3 which should be 0, delta 2 3 which should be 0, and then delta 3 3 which should be 1, multiplying A3, so that will be A3. So essentially, because of that, you know that we can easily just say that AI delta ij is equal to AJ. Think about that. Does that make sense? Because we have seen that the result at the end of the day essentially is going to be A sub whatever J is. So here J is 1. So at the end of the day, we got A1. J is 2 here, we got A2, and J3, we got A3. So then this entire expression can be seen as just AJ. Yep, that is an interesting result. There's also something interesting about the Kronecker delta, how we can simplify the Kronecker delta if we come across it. And that is the fact that when we look at the subscripts of the Kronecker delta and we see a term, sorry, we see some other figure or some other expression in the same term. Now this is a singular term. We have AI delta ij. So if it carries the same subscript as any of them, then we can let go of the Kronecker delta. When we let go of the Kronecker delta, we will then replace that common subscript by the other subscript of the Kronecker delta. That is a lot of grammar, I know. Let us repeat that again. Looking at this now, this has AI and we have delta ij. What are the subscripts of the Kronecker delta? I and j. What does it have in common with A? It has I. So we can forego or ignore the Kronecker delta, and the implication will be that the subscript that it has in common will now be replaced by the other subscript. So we will have I that it has in common, we replace it by j. So instead of having AI here, we have AJ, and then we let go of the Kronecker delta. So that is the interesting thing about the Kronecker delta and how we can simplify expressions when it is simplifiable, so to speak. um, we can simplify expressions that carry the conical delta in that manner. So, for example, again, another example, if we have, say, we have something like AI, BJ, and delta IJ. This is a singular term. All of these are being multiplied. What do you think this will be equal to? The question should be firstly, can we simplify this expression or this term? And the answer will be yes. And how do we determine whether it is yes or no? Look at the subscripts of the Kronecker delta. Do we have any other, do we have the subscripts repeated in the same term? And the answer here is yes. Why? Because this subscript I is repeated, it appears here as well. So this is subscript I, this is subscript I, it's appearing twice. Okay. Subscript J also appears twice. So that's interesting. It does not flout or break any of the rules we have discussed previously from the Einstein summation convention. This is J appearing twice. We said that no subscript should appear more than twice, so none of them is appearing more than twice. Okay, so this is J and this is J. This is I and this is I. So we can simplify this expression. By that we mean we can let go of this Kronecker delta or ignore it completely. And what will be the implication if we ignore it completely? So we will say, okay, if we are saying that I is what it has in common, we know it has I in common with this, it has J also in common with this, okay, but we just take one of them at a time. Okay, so if we say it has I in common, okay, I want to let go of the Kronecker delta, then we will have to replace that I it has in common with the second subscript here, which is J. So if that is the case, then we write this as what does it have is in common with? That's I in common with A. So we replace the subscripts of I here with the second subscript of the Kronecker delta, which is J. This will remain in place. So this will be PJ. Then we will ignore delta altogether because we have taken care of its implication, okay, its overall implication to this term. So this is equal to this as we have said here. So this is correct. Another way we can simplify this, you might have guessed, is that recognizing that, of course, we're repeating the same thing for instance for now. So recognizing also that it has J in common with this. So if we're going to let go of J, then we will have to replace it with the second subscript here, which is I. So this could as well be written as AI, meaning that we are not touching A and its subscripts. We're just relating the delta with BJ. So this will be AI multiplying BI. So we are letting go of J. So if we're letting go of J, then we have to replace it with the second subscript here, which is going to be I. So this is AIBI. So this expression here, which is AJBJ, is the same thing as AIBI. So both of them are correct. Okay. So this is AJBJ, and this is equal to AIBI. Of course, you don't need to be told that these two are the same because J is appearing twice here, it's a dummy subscript, I is appearing twice here, it's a dummy subscript. So essentially they have the same implication because they both mean that we do some summation from 1 to 3. So this is simply A1 B1 plus A2 B2 plus A3 B3. This is the same thing as well. A1 B1 plus A2 B2 plus A3 B3. Okay. The fact that they are repeated is sufficient. That's exactly what we need. It is not whether it is I or J or K that matters. What matters is it repeated? If it is repeated, then it's a dummy subscript, then it means a summation. Okay, so that is how we can simplify expressions that carry delta whenever we have any one of its subscripts to be bound by any of the other expressions written with it in the same term. Okay, so what if we have something like this now? Let's say we have another expression. Let's say we have A, I, B, J, and then we have C, K, then we have delta. Let's say this is delta J, L. Okay, this is delta J, L. So can we simplify this? So look at that closely. This is a single term. All of these are being multiplied. So we ask ourselves, do we have any of the subscripts of our Kronecker delta to appear elsewhere? And the answer to that is yes. We can see J is here and J is here. Does it have any other thing in common? No, this is L. L is not present elsewhere. So how do we simplify this? We have only one option. It has J in common with this. So if we're going to let go of the delta, then we will replace J that it has in common with its other subscript, which is L. So essentially, this will be equal to AI, and instead of BJ, we now write BL and then CK. So this is acceptable because of that. So we have then ignored the Kronecker delta by that. And these are all implications following from what we observed here. So you can convince yourself as well that if you actually did an expansion of this, okay, you will essentially get this result, okay, which you can write this way, okay. So that's that about the Kronecker delta. Let us quickly put this observation in words properly, and then we will move on from there and we will end the lesson there. We say that whenever a dummy subscript, whenever a dummy subscript is shared by the Kronecker delta, by the Kronecker delta, the dummy subscript, the dummy subscript can be replaced, the dummy subscript can be replaced by the other subscripts, can be replaced by the other subscripts, okay, on the Kronecker delta, by the other subscripts on the Kronecker delta with the and the Kronecker delta and the Kronecker delta ignored. So that is the idea. So why are we calling it dummy here? Dummy because it appears twice. Okay, that's what makes we have said by our rule that it cannot appear more than twice. No subscript can appear more than twice in a given term. So dummy means that it appears twice. So that's what we're saying. If it is shared by the Kronecker delta, that means one of its appearances is on the Kronecker delta. So that is the idea. So we see here I appears twice. One of them is on the Kronecker delta. So we can let go of the Kronecker delta, then replace that dummy subscript completely by the other subscript on the Kronecker delta. So we replace this I by J. So we have AJ, BJ, and then we let go, forget about the Kronecker delta. So that gives us this. And we have illustrated why that is here. So by this observation here also, we could have arrived at this directly if we made use of that rule. You can see this dummy subscript here is I. So by that, it is shared by the Kronecker delta. We can replace that dummy subscript by the other subscript. That would be J, and then forget about the Kronecker delta. So that gives us AJ, as we have seen. Okay, and the same thing applies here. Dummy subscript, where is it? This is J, this is J, it appears twice. That's a dummy subscript as by our definition, by our convention so far. So we can replace that dummy subscript J by L and forget about the Kronecker delta then. So that's exactly what we did here. The same thing here. If we say the dummy subscripts here are two, but we just take one of them at a time. Okay, so if we take this as that dummy subscript at this time, I will take J as that dummy subscript at this time. Then we replace it by the other subscripts on the Kronecker delta I. Then this comes here. So this becomes AI BI. So and that is that for now about the Kronecker delta. Again, as we proceed, we will see how this actually helps us to simplify some vector relations and actually make it makes our work easier when we're trying to prove some vector relations. So I'll see you in the next lesson as we discuss some other notation. Thank you for watching.